So I want to give you a quick explanation of Lewis dot diagrams and how to create them. You already know about atomic structure. We talked about the nucleus of an atom being made up of neutrons, which are neutral, protons, which are positive, and then electrons orbiting around the nucleus in the electron cloud, and they're negative. What Lewis dot structures are designed to do is show you this outside layer of electrons and how many electrons are there. And the reason is those are the ones that are involved in chemical reactions. The ones on the inside are never gotten to. So when you react something like hydrogen with oxygen to make water, it's the electrons on the outside of the atom that are actually involved in the chemical reaction. And they're the ones that we need to pay attention to because they determine how an element behaves when it reacts with something else. So we've talked about orbitals being like the previous picture where they're almost like planets going around the sun. And that's not really what they look like. They look more like this. The s orbital, which is the very closest level, is shaped like a sphere. And the p orbital, and the d orbital, and the f orbital, those are ones that are further out away from the nucleus. So you can see that it's a lot more complex than we describe it as typically, and this is not practical for us. And it really doesn't explain the chemical behavior of elements. So we simplify it and we make it look like an orbital with planets going around the sun. But again, not really all that accurate, just so you know. So what we do is when we draw these electron shells, they're called, or orbitals, we start from the nucleus and we work our way out and we name them. Now in this diagram it's called, Roman numerals, energy level 1, 2, 3, and 4. That's fine. They also have names, and that's what the K, L, M, and N. So we talk about the K shell, the L shell, M or N, or the K orbital and the L orbital. And these numbers are how many electrons will fit in each level maximum. Think of it as a glass that's tapered at the bottom. The bottom can only hold 2 electrons. The next level up can hold 8. The next level up can hold 18 and then 32, and then beyond that is 32 for each of the subsequent levels if there are any more, O, P, whatever. Now, you cannot put electrons into the L shell here until you fill up the K level below it. Just like when you get a glass of water, you can't fill the top half of the glass before you fill the bottom half of the glass because of energy. The lowest energy electrons are closest to the nucleus. So they're going to fill up these lower layers and then fill up these layers and then fill these layers up. Again, for those of you who know chemistry, this is a gross simplification. That's not exactly how it works, but it's close enough to explain what we're doing right now. So just remember 2, 8, 18, and 32, KLMN. So there are 2, 8, 18, and 32. Keep that in your head. Because when you look at the periodic table and you look at how many electrons each element has, you can then tell me how many of those electrons go in each level. For example, beryllium, it's element number 4, which means that it has 4 protons and it has 4 electrons. Those 4 electrons are going to go into those K, L, M, N, O orbitals this way. They're going to be 2 in the K shell and 2 in the L shell. So it has 2 electrons on the outside. We call those valence electrons. So beryllium has 4 electrons, 2 in the first level, 2 in the next level out. That's what this 2, 2 means. Sodium, element number 11, has 11 electrons. Now, that means there are 2 in the first level, there are 8 in the second level out, and that leaves 1 left over for the outside layer. So sodium has 1 valence electron. That, by the way, is what makes it so reactive. It finds other elements willing to take that electron, gives it away, and that's what makes it explode when you throw it in water and things like that. It's a very reactive element. Chlorine is also very reactive. It has 17 electrons, so when you count those up, that's 2 in the first level, 8 in the next level out, and then 7 on the outside. Okay, so it has 7 valence electrons. So now you know how to break them up into layers like that. And as you work along, you just keep going like that. You go, okay, 2, 8, 18, 32. How many go in each level? Just basically subtract 2, then subtract 8, and then subtract 18 until you run out. Those are the ones on the outside. Lewis dot diagrams are designed to show you just the ones on the outside instead of having to draw all these dots, because remember, the electrons in the inside don't really matter in terms of chemical reactions typically. So the K shell and the L shell here really aren't involved in reactions. It's the M shell that is reacting and causing the chemical reactions, releasing energy, absorbing energy, whatever's going on. So chlorine's 7 valence electrons are drawn around the symbol like this. And the pattern is typically go top, bottom, left, right, and then pair them up, top and bottom, left and right. But you can only draw 8 dots. Don't ever draw 17 electrons around this. You only draw the ones on the outside in the last shell. Those are the valence electrons, and those are the ones we're interested in. So any symbol in the middle is going to have a maximum of 8 dots around it. Something like carbon, which has 6 electrons, is going to have 2 in the first shell and 4 in the second shell out. So it's going to be looking like this: top, bottom, left, and right. Now, if there were 5, we would put 1 here, or 1 here, or 1 up here, or 1 down here. They pair up, top, bottom, left, and right. But just remember, if you follow the pattern, top, bottom, left, and right, everything will work out just fine for you. But remember, you're only drawing the outside. I would never draw 6 around this because these 2 on the inner shell are happy and content, and they're not involved in chemical reactions. So if you have any further questions, see your instructor, and we'll give you a little more practice in this.